Welcome to this session. In this session, we are going to discuss about applications of our Gauss law. Already we learned what is Gauss law. Now we will learn how to apply this Gauss law for different types of charge distributions. As we learned, this Gauss law is very much useful in electrostatics for observing or finding electric field as well as electric flux density. So it gives very simplest way to find our electric field intensity and electric flux density. Now we will observe what are different steps which are involved in our Gauss law. The steps involved in our Gauss law are, clearly remember, if you follow these steps, so we can find or we can observe our electric field intensity in an easiest way. So the electric field intensity can be calculated for any type of charge distribution using our Gauss law in very simple way. So what are the steps involved? Just you observe here. The first step is to form a symmetric Gaussian surface. Just what we need to do is we need to form a symmetric, this word is very important, a symmetric Gaussian surface around the charge what we are considering. On that symmetric Gaussian surface, the electric field intensity must be uniformly distributed. That we need to remember that point. So this is the first step for any type of charge distribution. After formation of the symmetric Gaussian surface, the second step is calculate the total flux leaving through the Gaussian surface. Here what we are supposed to do is we are supposed to calculate the total flux leaving through the Gaussian surface what we formed in our first step. This is the second step what we have to do. Third step is calculate the total charge enclosed within the Gaussian surface. Here step 2 and step 3, these two are very important steps. If you are able to find out what these two, then obviously the problem is over. That calculate the total flux leaving through the Gaussian surface and calculate the total charge enclosed within the Gaussian surface. And as per our Gauss law, these two are same. That is 2 is equals to 3 will gives us the required equation or the required quantity for us. That may be electric field intensity or that may be electric flux density, right? So if we adopt these three steps, then obviously the equation is very simple to identify or find out for any type of charge distribution. Now we will apply our Gauss law for different types of charge distributions starting from point charge to volume charge. So first we will discuss about the point charge. Now we will start our application with point charge. Now let us consider we have a point charge. Because of that point charge, what will be the electric field intensity at a particular point in space? That's what we want. Already we discussed this one in our Coulomb's law. Whenever we have a point charge Q, the electric field intensity at some point P already we obtained as E is equals to Q by 4 pi epsilon naught R square in the direction of that R, where R is the distance vector which is drawn from charge to point P. Already we obtained this. Now we are going to obtain the same equation using our Gauss law, that we can learn how to identify or how to obtain that equation in an easiest way using our Gauss law. That what I do is I will try to derive the same equation E using our Gauss law with the following by following the steps what we discussed just now. Now the first step is to form a Gaussian surface. That Gaussian surface must be the symmetric Gaussian surface on which the electric field intensity is uniformly distributed around the charge. That let us take, this is the charge what we have, a point charge Q we have. Around the positive charge at every space, in the space at every point, the electric field must be uniformly distributed and we require a symmetric surface. That we have imagination plays very important role. We need to imagine Let us take this is the point charge what we have. For this point charge, if you form a symmetrical surface, then obviously a spherical shape is the surface what we get. So a spherical shape like surface is the most appropriate one, that will be called as the Gaussian surface. Now what I do is I will take a spherical space or spherical surface around this charge. I will call this one as Gaussian surface. So clearly a Gaussian surface was now formed. Now we have to calculate the total flux leaving through that Gaussian surface. How much flux is leaving through that Gaussian surface because of this charge, right? So let us take, that is the second step what we have to do. Let us take, this is the direction of our flux which is passing through the Gaussian surface. We need to calculate the total flux. For that what I do is, I will take the differential surface on this particular Gaussian surface. I will integrate the differential surface along with the flux density. So for that let us assume the flux density what we have is d is equals to d in the direction of radius, that is dr in the direction of radius. Now if you take this flux density and using this flux density easily we can calculate the total flux leaving through that particular surface. So already we have a relation that the total flux leaving is equals to the integral here, since it is a closed surface, what we need to do is we need to take the closed surface integral of d with respect to that differential surface. So what we have to do is just we have to substitute d here and we have to substitute ds here, and after simplification we can get the total flux leaving, that what we can calculate, right? Substitute d here, so which is nothing but the closed surface integral of d is dr ar dot, a dot product is there, ds. Here what I do is just I will give you a simple method, don't go for any formula, that just you observe the differential surface and just you write down the equivalent of the differential surface here, don't go for any formula. Once again I am saying, right, differential surface of the Gaussian sphere is in the direction of radius. So here what we have to do is differential surface for the Gaussian sphere in the direction of radius is ds in the direction of radius is ar, that what I am considering, that simply it is ds ar. This must be observed, don't write the equation, just dr ar is the flux density what we have. So we are integrating that flux density for the entire surface, that is our Gaussian surface ds ar. Now ar dot ar is always 1, so which is equals to surface integral of, it is closed surface integral of dr with respect to ds. Now as we discussed, this dr is uniformly distributed. So on the Gaussian surface what we are considering, electric field intensity is uniformly distributed. Since the electric field intensity is uniformly distributed, electric flux density is also uniformly distributed. So bring it out from the integral. So no problem, just we bring it out from the integral, then what we get is dr a closed surface integral of ds. So clearly what is the closed surface integral of ds here? We are trying to obtain the total surface area. That surface integral of ds will gives us the total surface area of the sphere what we considered as Gaussian sphere or Gaussian surface. So clearly directly we can write down the equation, a mathematical equation for this one. We know what is the surface area of a sphere, it is simply 4 pi r square. So just take the radius of our Gaussian sphere what we formed as r and replace the surface area here. So that is surface integral of ds can be replaced with 4 pi r square. So this can be written as dr into 4 pi r square. So the total flux leaving is now equals to dr into 4 pi r square. So that is our step 2. That is we calculated the total flux leaving through the Gaussian surface. Right, here clearly observe this flux is not a vector quantity, this is clearly a scalar quantity, so that there will be no direction or vector here, remember that. Next, third one, we are supposed to calculate the total charge enclosed within this, that this is the Gaussian surface what we have. In that Gaussian surface just observe how much charge is there within that particular Gaussian surface. Since we are considering a point charge q, the total charge enclosed within that Gaussian surface is q itself. So as our third part, the total charge enclosed, that I will take the total charge enclosed as Q enclosed, which is equals to the point charge what we have, Q. So now what I do is just I will equate the step 2 answer and the step 3 answer. In our step 2 what we got, that dr 4 pi r square, that is the total flux leaving through the Gaussian surface. In step 3 we calculated the total charge enclosed within that Gaussian surface. The total charge enclosed within that Gaussian surface is Q. So if we equate these two, so clearly we get dr is equals to the flux quantity is equals to Q by 4 pi r square. So before that we defined d as d is equals to dr in the direction of ar. From that clearly we can write the total flux density is equals to Q by 4 pi r square in the direction of ar. So this is the total electric flux density what we have because of a point charge. If we know the flux density, easily we can obtain the electric field intensity. So we have a relation d is equals to epsilon naught E. From that E is equals to d by epsilon naught. Therefore clearly the electric field intensity equation can be written as Q by, this is nothing but total d 4 pi epsilon naught r square ar. So now observe the electric field intensity what we got using our Coulomb's law is Q by 4 pi epsilon naught r square ar. The electric field intensity what we got using our Gauss's law is also same Q by 4 pi epsilon naught r square ar. So here if you observe the procedure what we adopted for this point charge is very easy. That not only to the point charge, if you take any type of charge, that if you want to just observe the electric field because of that particular charge distribution, we need to form a Gaussian surface, calculate the total flux leaving through that Gaussian surface and calculate the total charge enclosed within that Gaussian surface, equate them. It's a very simple one, just within that 3 or 4 steps we can obtain the solution, right. Now we will discuss the same concept for or the same adopt the same method for different charge distribution like line charge and surface charge. Now we are trying to apply our Gauss law for line charge. For our convenience what I do is I will take a line of length L. Let us take this is a line of length L and on that line the charge was uniformly distributed. So clearly the charge density will be represented with its line charge density rho L Coulomb per meter. So let us consider once again a line charge of length L and the charge density of that line charge is rho L Coulomb per meter. Now we are trying to obtain what is the electric field intensity because of this particular line charge. For that once again try to form a symmetrical Gaussian surface. The symmetrical Gaussian surface along the line, just imagine this is the line what we have. So if you try to form a symmetrical surface on this particular line, then that must be a cylinder. That cylinder consists of 3 surfaces, that is this curved surface, a top surface and bottom surface will cover our line charge. That imagination is required here. So what I do is I will try to form a particular cylinder with some radius r or rho around this line charge. So let us take rho is the radius of this cylinder. Around that line charge I will form a cylinder, that this cylinder is now will be treated as Gaussian surface. So remember in our point a sphere is the Gaussian surface, but in the case of line Gaussian surface is a cylinder. Now observe how many surfaces are there for this cylinder. One top surface is there, bottom surface is there and then one curved surface is there. Now we are supposed to calculate once again the total flux leaving through the surface and the total charge enclosed within that particular surface, right. So the step 2 is total flux leaving through the surface, that is psi. As already we know, the psi can be calculated using one and only formula, that is closed integral of dds. Since it is a closed surface integral of ds will give us the total flux leaving through that particular surface. Now how many surfaces are there? Once again I said the 3 surfaces are there, one curved surface, one top surface and one bottom surface. Now observe the direction of d with respect to this surface. Always for a line the d is in the radial direction, that what we can say. Since the d is in radial direction, So for any other directions of this surface, if you are considering dds, we may not get the exact answer, so we may get some other answer, right? We may not get 1 for the dot product, we may get some other thing. Just we will examine. Let us take for the curved surface, this is the direction of d and this is the direction of ds. So both are in same direction. So this is the direction of d, this is the direction of ds. So when you are doing this dot product, so for the unit vectors, what we get is 1. So leave it. Now this is the direction of d, and for the top, this is the direction of ds. And if you observe clearly, this d and ds are orthogonal, that's a perpendicular to each other. Since these two are perpendicular to each other, this dot product now becomes 0. In the same way, if we consider this bottom, this is the direction of ds for the bottom, and this is the direction of d. So if you take the dot product between d and ds, what we get is once again 0. So clearly observe, the dot product between d, ds for the curved surface only exists. For the remaining two, that is nothing but the top and bottom, we will not get anything. So this closed surface now becomes open surface with one and only one, that is the surface for curved d, ds, that what I wrote. Just this is the observation, that what we are doing. We are not taking any equation. Now which is equals to, this s curved is nothing but, just write down this one as s, d is in the direction of rho, that what I do is, I will take this one as d rho a rho dot, s is ds is also in the same direction, that is nothing but the radius direction. So take this one as ds a rho. So d rho a rho dot ds a rho. So what is the answer? The surface integral of d rho ds. So as we discussed in our previous one, surface integral d rho ds, we will get the answer d rho surface integral ds. This d rho is uniformly distributed, that's why I brought it out from the integration, and this surface integral ds will gives us the total surface area of the cylinder. Just the total surface area of the cylinder for curved surface we must consider. So don't consider the top and bottom, as we ignore them, so don't consider them, just the curved surface we are considering. So the total curved surface area is d rho into 2 pi rho L. So as we assumed the length of our cylinder as L, or the line charge as L, just the total curved surface area is d rho into 2 pi rho L. That is our second step. We calculated the total flux leaving through the surface. And the third step is total charge enclosed. Here in our previous example, we took a point charge, that's why the total charge enclosed is directly equals to that point charge. But here directly we are not taking any charges here. Instead of that one, we are taking a charge density. So using that charge density, we can calculate the total charge enclosed within that one. So how to obtain the total charge using our line charge density? So line integral of rho L dl. It's a very simple one. Line integral of rho L dl gives us the total charge enclosed within that particular Gaussian surface. Already we assumed that the charge is uniformly distributed along the charge. Since it is uniformly distributed along the charge, take it as rho L, so line integral of dl, right? So rho L line integral of dl. A line integral of dl always gives the length of that particular line. So which is nothing but rho L into L. So see, it's a very simple one. So what we did is we calculated the total flux leaving through that one, that is d rho 2 pi rho L, and the total charge enclosed within the Gaussian surface, that is simply rho L into L. So as per our Gauss law, equate these two. So if you equate these two, what we get is the answer. So if we equate these two, so the total flux leaving through the Gaussian surface is d rho into 2 pi rho L, which is equals to the total charge enclosed within that one is rho L into L. Don't get confused. This rho is the radius of the cylinder, that what we discussed in our cylindrical coordinate system. This rho L is the line charge density. The suffix L always describes the charge density. Rho L into L. L is length of the cylinder what we have. L will be cancelled. Therefore, d rho is equals to rho L divided by 2 pi rho. As we discussed, this d is in the direction of our radius, that's d can be written as the flux density, electric flux density is equals to rho L by 2 pi rho in the direction of a rho. So clearly observe this differential electric flux density. This electric flux density is independent of length of the charge what we are considering. So whatever it may be the length of the charge, even if it is infinite line length, then clearly, so rho L by 2 pi rho A rho is the answer what we get here. So from this one we can obtain electric field intensity. So the electric field intensity can be simply obtained using this one, that is 2 pi epsilon naught rho A rho. So the different equation, that's what we got here, the equation of electric field intensity and the equation of our electric flux density. These two can be easily, very easily obtained using our Gauss law for line charge. Now we will discuss one more example, that is surface charge. Now we will examine. So what is the electric field intensity because of a surface charge when the charge is uniformly distributed over it. So for that, what I do is, for our convenience, I will take a surface or sheet that's along the xy plane, on the xy plane, exactly on the xy plane, and because of that surface sheet, what will be the electric field intensity at a point P in free space. So let us draw how the sheet was placed. So for our convenience, I will take our Cartesian coordinate system xyz, and on the xy plane an infinite sheet was placed. Just you need to imagine that one in a three-dimensional one. The sheet was placed on xy plane, right? Since the sheet was placed on xy plane, we are supposed to observe the electric field intensity maybe above the sheet or below the sheet. That is, at some point P in this space we are trying to observe the electric field intensity. Let us take, at this point P we are supposed to calculate the electric field intensity. Now how to apply our Gauss law? Once again, just we need to form a Gaussian surface. That Gaussian surface must be a symmetric Gaussian surface around the charge what we are considering. Since it is a flat sheet, so nothing is symmetric for that particular flat sheet. So approximated one may be cuboid. So what we have to do is, we need to form a cuboid around the flat sheet what we are considering. For that, for our convenience, what I do is, I will take a differential area. Let us take a differential area consists of charge density rho s coulomb per meter square. That is the surface charge density what I am considering. Let us take the area of this one is A. So here for our convenience, what I do is, I will take a differential surface, and now I will try to form a Gaussian surface around this differential surface. As we said, around this differential surface, if we form a cuboid, that may be approximately symmetric one. That may not be exactly, but that may be approximately symmetric one. So what I do is, I will try to form a cuboid around this. So let us form a cuboid like this, that at some point P, that's where we are going to calculate that point P is on that particular surface, Gaussian surface. Now this cuboid is said to be the Gaussian surface. Now observe how many faces are, or how many surfaces are there for this cuboid. If you observe clearly, this cuboid contains 6 surfaces. Since it is a closed surface what we are considering, so this will contain 6 surfaces, that is the top surface, bottom surface and 4 side surfaces. Just observe them. So here we have clearly the top surface, bottom surface and 4 side surfaces. Now with respect to those surfaces, what will be the direction of our flux density what we are considering? For any surface, just you observe the flux density is perpendicular to it. The flux density is always away from the sheet. So the flux density may be in this direction, that what you can say, this may be the direction of D, or the flux density may be in this direction. So here clearly for this particular sheet, the flux density may be in this direction and in this direction, and clearly remember, there is no flux density which is parallel to the sheet, right? Now with respect to this D, what are the directions of our surfaces we have? This surface, that is nothing but the top, is parallel to D, that what we can say, and the direction of this surface, that is nothing but the bottom, is also parallel to D, that what we can say, and we can observe the direction of this side is perpendicular to D. The direction of this side is also perpendicular to D. The direction of third side perpendicular to D. The direction of fourth side, that is also perpendicular to D. So clearly if we observe, only top and bottom will have a parallel directions to D, and the remaining 4 directions are perpendicular to D. Since they are perpendicular to D, when you are taking the dot product between them and D, so obviously the result is 0. So clearly observe here, the D contribution will be from only top and bottom. It's not from the remaining 4 sides, right? So Gaussian surface is over. So as our second step, calculate the total flux leaving. That the total flux leaving is initially closed surface integral of dds. But from our observation, clearly we can say that this closed surface integral is now becomes open surface integral with only 2 surfaces, that is the bottom surface and top surface. So this I can write as the surface integral of d ds, d dot ds that I write, plus this is because of the bottom d ds. And directly observe, don't go for any directions. D and ds are in the same direction, that is normal to the sheet. Here also D and ds are in the same direction, normal to the sheet, right? So that what I do is I'll take it out from the integration. So this is top ds plus d bottom ds. That what we have to do is just we need to observe what is this particular quantity. Integral ds will give us the surface area of the top. Integral ds will give us the surface area of the bottom. Since we are forming a symmetric one, the surface area must be equal to the surface area of this particular patch what we are considering, differential surface. We assumed that the area as A. So the area of top is equals to A, the area of bottom is also equals to A. So simply replace this one with A. So dA plus dA, which is equals to 2dA. Clearly remember, this D is normal to the surface what we are considering. So with this observation, clearly immediately easily you can calculate the total flux leaving through the surface of our cuboid. And the third one, the total charge enclosed. So what is the total charge enclosed? So easily you can calculate the total charge enclosed using its surface charge density. Since we have a surface, the surface charge density is the useful one. So the total charge enclosed is equals to surface charge of rho s ds. Since this rho s is uniformly distributed, bring it out from the integration, which is equals to rho s surface integral of ds. So rho s surface integral of ds, this surface integral of ds is nothing but the surface area of the differential area what we considered, that is nothing but A. So simply it is rho s into A. So just observe here, this is the total flux leaving through the surface 2dA. This is the total charge enclosed, which is equals to rho s into A. So as per our Gauss law, the total flux leaving is equals to the charge enclosed. So make these two equal. That is, the total flux leaving is equals to 2dA, which is equals to the total charge enclosed rho s into A, where A is the area of the surface what we considered. So this can be cancelled. Then D is equals to simply rho s by 2. Now the direction of D, if you want the exact direction of D, it is rho s by 2 into, so the direction is always normal to the sheet what we are considering. So from this one we can obtain E also. So E is equals to rho s by 2 epsilon naught an for free space. So if you are considering any other medium, just this epsilon naught will be replaced with that particular medium. So here clearly observe, we obtained the electric field intensity equation because of a sheet, an infinite sheet. This what we can observe. Whatever may be the sheet size, clearly the sheet will contribute rho s by 2 epsilon an at a particular point. So this is the electric field intensity which can be contributed by our sheet. So a very easy procedure, just we adopt so 1 or 2 steps, and if we examine them, how they will happen and how they come, so very easy to observe electric field intensity. Now we will take same example for volume charge also. Now we will examine what will be the electric field intensity because of a volume charge. For our convenience, what I do is I will try to take a spherical volume. Because of that particular spherical volume, what will be the electric field intensity? So let us take a spherical volume is available with us. Since it is a spherical volume, So the volume charge density is available. So there is no absolute charge. So instead of that absolute charge, we have volume charge density. Let us take the volume charge density within this one is rho v coulomb per meter cube. Right. Now we are supposed to observe what will be the electric field intensity because of that one. The electric field intensity because of this particular spherical volume can be observed in two different regions. One is within this spherical shell what we have to take, and that's outside the spherical shell what we took. So clearly these two are the two regions what we have. For our convenience, let us take the radius of our spherical shell as A, and at different locations we are observing, once again we are observing our electric field intensity. In the case 1, let us take the electric field intensity inside the sphere what we considered. Since this is the sphere what we are considering inside the our original charge what we have, the Gaussian surface what we are forming is also inside that particular charge what we are considering. And it's a most probably, it's not most probably, it's always the Gaussian sphere what we are considering is a sphere. Since the volume what we are considering is a sphere, the Gaussian surface is also a sphere. So let us take this is the Gaussian surface with some radius r. So a Gaussian surface with radius r we are considering inside the charge what we took. Right. Now we need to obtain what will be the electric field intensity here. So for that what we have to do, once again calculate the total flux leaving through the Gaussian surface. Here remember, don't take our original charge while calculating the total flux. Just always consider the Gaussian surface only while calculating the flux. And so while calculating the charge, if it is necessary take the charge, otherwise so within this one just you calculate how much charge is there, nothing more than that, right? Now calculate the total flux leaving through this one, and from our observation always the flux leaving through this one is in radial direction. So clearly you can write the flux density D is equals to dr in the direction of radius AR. So D equals to dr here, that what we have. Now calculate the total flux leaving. So total flux leaving is nothing but psi is equals to closed surface integral of d ds. Now which is equals to surface integral of d is dr AR dot, what is the direction of our surface? It's also in the direction of radius. So don't go for any equation, just you observe here, nothing more than that. So it is also in the direction of AR. So AR dot AR is 1. So dr is uniformly distributed. So clearly you can write dr surface integral of ds. So surface integral of ds is nothing but the surface area of the Gaussian sphere what we considered. So the Gaussian sphere radius is r. So clearly this entire term can be replaced with 4 pi r square. That is nothing but the surface area of the Gaussian sphere. So this can be written as dr into 4 pi r square. The total flux leaving through the Gaussian sphere we calculated now. In the same way, total charge enclosed within that Gaussian sphere also we require. So that is our next one. So total charge enclosed, that is Q enclosed is equals to. So how to calculate this total charge enclosed? Using our volume charge density up to this particular region only. So here clearly remember, don't consider the charge within this particular space which is not meant for us. So we are supposed to calculate the total charge enclosed up to the Gaussian surface only, right? So Q enclosed is equals to, here also this is the total charge can be calculated using volume integral of, that since we are considering a volume integral of rho v dv, right? Rho v is uniformly distributed, therefore it is rho v into volume integral of dv. Now what is the dv? The volume, it's a differential volume is integrated, so we will get the total volume. This total volume is the volume which is covered by the Gaussian surface, right? Since the Gaussian surface is a sphere, definitely it forms some volume. That volume we are supposed to observe here. Once again I am saying, don't go for any formula or calculation, just observation is important, that this is the volume which is covered under the Gaussian surface, right? Which can be written as simply rho v into, what is the volume of our sphere? 4/3 pi r. So already known to us. So clearly it is 4/3 pi r cube. So once again just observe what we are doing here. We are calculating the total flux leaving through the Gaussian surface and we are calculating the charge enclosed within that Gaussian surface only. Don't go for outside of the Gaussian surface, we don't bother about that. We are supposed to consider only the volume within the particular Gaussian surface. That's why we got rho v into 4/3 pi r. Now as per our Gauss law, these two are same. That is the total flux leaving dr 4 pi r square is equals to rho v into 4/3 pi r cube. That dr 4 pi r square is equals to rho v 4/3 pi r cube. So after simplification what we get is simply dr is equals to rho v into r divided by 4 will be cancelled, pi will be cancelled, 3. So rho v into r by 3 is the equation for our electric flux density. Now what is the direction of this d? If you want to write down d, dr ar, that is rho v r by 3 in the direction of r. So just observe here, the electric flux density is directly proportional to r. That is whenever we are moving towards this sphere within that particular sphere, the electric flux density increases, right? Clearly observe that particular point. From this one the electric field intensity also can be calculated using this rho v by r 3 epsilon naught a r for our free space. Now this case is a very peculiar case that we are calculating the electric field intensity within the volume what we are considering. Since we are calculating the electric field intensity within the volume, here we need to take a little bit care. The total flux leaving through the Gaussian surface we calculate up to this radius and the total charge enclosed also calculated up to this radius only. So whatever may be the radius of our sphere, just we considered for our Gaussian surface only. So clearly we can observe the electric field intensity is rho v into r by 3 epsilon naught r. Now we will move to the second case, that if the electric field intensity is observed outside this surface, so outside the charge what we are considering. Now let us consider second case, that what we are doing is we are trying to obtain what will be the contribution of this particular volume charge in electric field intensity outside of this charge, right? For that, if you form a Gaussian surface, a symmetrical Gaussian surface around a sphere, once again the symmetrical Gaussian surface is a spherical shape, right? So here what I did is I took a Gaussian surface, what we took is in the spherical shape with some radius r, and same as our previous one, let us take the volume charge density is rho v coulomb per meter cube. So the formation of Gaussian surface is over. Next calculate the total flux leaving through the Gaussian surface. The total flux leaving through the Gaussian surface is also in the direction of radius. So don't go for any other equations. Once again take this d as just dr in the direction of radius dr ar. So what is the total flux leaving? Psi is equals to, so this is our second step, psi is equals to a closed line integral of, so d ds, it's a surface integral of d ds, that what we have. Now which is equals to closed surface integral of, instead of d write down this dr ar dot, and what is the direction of surface? The direction of surface is always in the direction of radius. So you can take this ds as ds ar. Since it is in the direction of radius, I took this ar as unit vector. So closed surface integral of dr ds, as we discussed, this dr is uniformly distributed, bring it out. So it is dr closed surface integral of ds. Now what is this closed surface integral of ds? The differential surface was integrated to obtain the total surface area of Gaussian sphere. It's not up to the charge, just what we are considering is the from Gaussian surface how much flux is leaving. That's why we are supposed to take the surface area of the Gaussian surface what we took. Gaussian surface has a radius of r. So what is the surface area for Gaussian surface? So dr 4 pi r square. So clearly observe here, the total flux leaving through the Gaussian surface is equals to dr 4 pi r square. Next, as a third step, we are supposed to calculate the total charge enclosed. The total charge enclosed can be calculated using its volume charge density, right? So take this volume charge density and integrate it over to get the total charge So over the volume to get the total charge. So volume integral of rho v dv gives us the total charge. Since this rho v is uniformly distributed, rho v volume integral of dv. That now observe this volume integral of dv. This volume integral of dv is nothing but the total volume of the charge what we are considering. So don't get confused, this volume is for the charge and this surface is for the Gaussian surface, right? The charge is confined up to this particular radius only, that is up to a only the charge was confined. So here the volume must be considered up to a only, right? So clearly write down the equivalent volume of the charge what we have. Since the radius is a, it is 4/3 pi a cube. So the total volume of the charge what we are considering is just 4/3 pi a cube. Here it is the total surface area of the Gaussian surface. Now as per our Gauss law, so these two are same, make them equal. That dr 4 pi r square is equals to the total charge enclosed is rho v 4/3 pi a cube, right? Now dr is equals to, clearly you can write down the equation for this dr as rho v by 3 a cube by r square. So d can be written as d is equals to, along with its direction, rho v by 3 a cube by r square along with its direction ar. This is the equation of d, and the equation of E can be written as EV is equals to rho v by 3 epsilon naught a cube by r square ar. So clearly observe, these are the equations of our electric flux density and electric field intensity in case the electric field intensity or flux density is observed outside the volume. So now if you observe, this E is inversely proportional to r square, or D is also inversely proportional to r square. In just previous case what we observed is D and R are directly proportional. In this case what we observed is E and R, or D and R are inversely proportional to each other. So if you try to draw the graph between the point where we are observing the electric field intensity and the strength of that particular electric field intensity, the graph will be like this. That here I am observing the electric field intensity E or D, so with respect to this R. So from origin, that's a center point to up to A, so those two are directly proportional. That as R increases, E also linearly increases. That up to point A, so it will be linearly increases. And after that one, it is inversely proportional to R, that is E is proportional to 1 by R square. Since it is inversely proportional, as R increases, it decreases like this. So clearly at this particular point, it attains its maximum value. So this is a simple observation, and using this procedure what we adopted for the calculation of our electric field intensity, we can obtain the electric field intensity for any type of charge distribution, that may be point charge, line charge or surface charge. So clearly we can obtain the electric field intensity because of that one using these simple 3 steps, that calculates formation of the Gaussian surface, and then calculate the total flux leaving through the Gaussian surface, and calculate the total charge enclosed within that Gaussian surface. So while calculating the charge, just we are supposed to take up to the Gaussian surface, don't take the charge which is outside the Gaussian surface. We need to remember that particular simple point. So with this one, it's a different applications of our Gauss law are over. So while solving the problems directly, we can use this formulae. Now we will examine one more special case, that what will be the electric field intensity because of a ring. That's whenever we have a ring which is placed symmetrically on some xy plane, then what will be the electric field intensity because of that. This is a very simple and special case. So let us take a ring is placed symmetrically on xy plane. So a ring was placed, or a loop was placed symmetrically on xy plane. Now we are supposed to calculate what will be the total electric field intensity at some point P which is on z axis. Since it is on z axis, let us take this height as h. The coordinate of this one is 0, 0, h. Let us take the radius of our ring as some a. So here we have a ring of radius a and a height h, at height h we are calculating the electric field intensity. This is the point of observation. Now simply what we have to do is we need to calculate the total charge, so around this loop, and what is the distance between these two. It's a little very simple procedure is there. Just observe here what we are doing. What is the basic equation of electric field intensity? The basic equation of our electric field intensity is Q by 4 pi epsilon naught r square in the direction of r. So that is the basic equation. Now what we do is we will try to change this equation by observing different quantities. What is the charge we have here, and what is the AR unit vector from the line charge to the point of observation, and what is the distance vector from the line charge to the point of observation. Since it is not a linear line, what we do is we will try to take a differential element at some particular point, and we will try to integrate this differential element throughout the length of our ring. That what we considered. So consider a differential element here. Now this is the direction of the differential element, and consider the direction of A also. This is the direction of A, it's along the radius. Consider the direction of H also. This is the direction of H. And if you take the distance vector from the differential element to the point of observation, then this will be the direction of differential vector R. So simply we need to obtain what is this R and what will be the total charge on the line what we have, nothing more than that. Now first what I do is I will try to obtain the total charge. The total charge can be obtained from its charge density. It is not an absolute point charge, just it is a line charge. Since it is line charge, so we need to consider the line charge density rho L. So using that rho L we need to calculate the total charge. So what I do is Q can be replaced with just Q is equals to integral rho L dl. Now this rho L is nothing but the line charge density, line integral dl. This line integral dl will give us the total length of the line. So what is the total length of the line? Just if you take the radius as A, the total length of the line is 2 pi into A. So the total line length can be simply replaced with 2 pi A, nothing more than that. So instead of Q, what we have to do is just we need to take the equivalent of that Q. So with this rho L into 2 pi A, the part is over. Next try to obtain this R. So if you take this R as a vector, that will be more convenient. So what I do is I will take this triangle. So let us take this is origin O DL point P. So consider this triangle O DL point P. In that what we have are different vectors. This is vector A, this is vector P, and this is vector R. This is vector H, that what we can say. This is vector R. So if you take the vector notation and if you take the addition of two vectors, that is minus A in the direction of rho and H in the direction of Z. That what I am considering. Clearly observe. Minus A in the direction of rho, or A in the direction of minus rho and H in the direction of Z. The vector addition gives the equivalent R. So clearly R can be written as R is equals to minus A arrow plus H AZ. That what we have. Now what is the magnitude of this R? R is equals to under root A square plus H square. Nothing more than that, just substitute here. And A can be written as, the unit vector also can be written as AR is equals to R by magnitude of R, which is equals to minus A arrow plus H AZ divided by under root of A square plus H square. Just substitute these values here along with this Q. So what is our electric field intensity? Electric field intensity is equals to Q is rho L 2 pi A into AR. AR is minus A arrow plus HAZ divided by 4 pi epsilon naught. 4 pi epsilon naught R square. R square is A square plus H square into, in our AR one more term is left for us, that is under root A square plus H square. Just what I did is I took the equivalent of this Q, I took the equivalent of AR, I took the equivalent of R and substituted here. So after the substitution what we got is this equation. Rho L into A divided by 2 epsilon naught, and the numerator term is minus A aero plus H Az divided by denominator is A square plus H square whole power 3 by 2. Just examine this equation. The electric field intensity has two components. So the one component is along rho, another component is along z. That the equivalent has a rho component as well as z component. But if you observe this dl is located somewhere here, right? The same amount of the electric field intensity can be observed in the opposite direction also. That if you consider the symmetry of the ring, you may have another one in the opposite direction to this previous quantity. So because of that symmetry, all the rho terms can be cancelled. So whenever we have a particular electric field intensity in this direction, because of the symmetry, you may have the same electric field intensity in opposite direction in our rho direction. So clearly observe, so this rho term can be cancelled. So make it equals to 0 and rewrite the equation of our electric field intensity. So our electric field intensity equation is now E is equals to rho L A, and here what we have is H in the direction of Z divided by 2 epsilon naught A square plus H square whole power 3 by 2. So this is the equation of our electric field intensity because of a symmetrically placed ring. And here clearly observe, we are calculating the electric field intensity along the axis of this ring. So this is a case what we took, that the ring is placed on xy plane. If you are supposed to generalize that one, it's clearly observe the direction of the electric field intensity is normal to the ring plane. That's a normal to the plane containing the ring, and A is nothing but the radius of the ring. H is the distance between center of the ring to the point of observation. That we need to generalize like that. Instead of this Az, what we are supposed to do is we are supposed to take the normal direction for this particular ring. This is a simple special case that what we can observe, and we can calculate the electric field intensity for different types of charge distributions.